In this screencast, we'll continue talking about Euclid's second theorem. So let's reformulate this theorem. Just give another formulation to it. You can watch the previous screencast on this and check the previous formulation. So we decided that we're going to define primes as p0, and we start from 0. Well, technically it's not a prime, but this is just the base case of upcoming primitive recursive definition. And we have also we're going to define Euclid's number as the factorial of the nth prime plus 1. Right, in the previous screencast, it was defined as the product of the previous primes. But we can also define it as a factorial. And so this reformulated second theorem by Euclid states that En is either a prime or is divisible by a prime greater than Pn. Okay, so the nth prime. So there are infinitely many primes. So and the proof is that if En E sub n is a prime, we're done because obviously it itself is greater than the nth prime. If it's not a prime, then En is a composite. And then it has a divisor, a prime divisor, greater than Pn, because it's a natural number. Every natural number has a prime divisor, and by a number theory factoid that we discussed in the previous screencast on Euclid's second theorem, it cannot be any of the primes from 2 to Pn. So it's not divisible by 2, 3, 4, 5, and any of the primes up to Pn. So where can the next prime be found? Right. Again, we let's say we have computed the ith prime. Let p sub I be the ith prime, and we would like to compute the I plus first prime. And so what is that prime? What is the next prime number? And more importantly, where is the next prime to be found? It's an important question because if we can put an upper boundary on where the range of where the next prime is to be found, then we can use the bounded minimalization, and the bounded minimalization of primitive recursive functions is itself primitive recursive. And so that's our plan. Well, first the lower bound is pi plus 1. Right? So for example, p sub 1 is 2, and p sub 2, the second prime, is 2 plus 1 is 3. Right? So we can start looking for the I plus first prime, just adding 1 to the current prime, right? Prime number I. So the lower bound is p sub I plus 1. So what's the upper bound? And this is what Euclid's gift to computer science is. It's this upper bound on the next prime. Right, and it is p sub I factorial plus 1. Why? Well, because p sub I factorial plus 1 must have a prime divisor. It's a natural number greater than p sub I. So because p sub I factorial plus 1 has a prime divisor greater than p sub I. Okay. So let's, to make this more concrete, let's go through a couple of examples. So this is our base case, and the first prime is 2, which is can be found in this range, 0 plus 1, a lower bound, and the 0 factorial plus 1. And well, this range is 1 and 2, right? Inclusive, so closed range, closed interval. The second prime is can be found in the interval 2 plus 1, so the previous prime plus 1, and the upper bound is the factorial of the previous prime, which is 2, plus 1, so it's going to be between 3 and 3, and it is 3. Now the third prime will be found in this range. The previous prime plus 1 and the factorial of the previous prime plus 1. And this range is 4 and so 7, yes. So, and 5 is between 4 and 7, inclusive, closed interval. So the fourth prime is 7, and that's the previous prime, 6 plus 1, so 5 plus 1 is 6, and the factorial of the previous prime, which is 5 factorial plus 1. So that puts us from 6 to 121. Okay, and so forth. So, and that gives us enough equipment to answer this question, that to prove actually that computing primes is primitive recursive. Not just testing primality, which we previously proved, but effectively computing all of the prime numbers. So given p sub I, like the ith prime we have computed, for example, then the next prime will be found in that range. P sub I plus 1, lower bound, and p sub I factorial plus 1 on the upper bound. We're going to show, using this fact, Euclid's gift to computer science, p sub n is primitive recursive. So p sub 0 is 0, and p sub n plus 1. We're just going to write a simple recurrence. Well, two simple recurrences. That's the base case, the first one, and the second is the recursive case. T less than or equal to p sub n factorial plus 1. Using that fact, right, that's the upper bound of this predicate, minimalization of bounded minimalization of this predicate, prime t, which is, okay, let me grab a different color. This is primitive recursive. We have shown that to be primitive recursive, and this is also primitive recursive, assuming that p sub n has already computed. Greater than is primitive recursive, and end of two primitive recursive predicates is also primitive recursive, so this is a bounded minimalization. On the assumption that p sub n is computed, then less than or equal to is also primitive recursive, and the bounded minimalization of a primitive recursive function is primitive recursive itself. Okay, so that's the proof, and then we can formalize this proof. So by defining this predicate h lower upper equals to, and the minimalization of t less than or equal to upper, and then the predicate is prime t, and t is strictly greater than lower. Okay, so and given this, we can define this function k of x in terms of h is obviously primitive recursive, um, right? X and x factorial plus 1, the lower bound and the upper bound. And then now, given k sub x, we can rewrite p sub I in terms of k of x. P sub n plus 1 is equal to k of p sub n. So, and this is primitive recursive.